Our project is the National Trust headquarters in Swindon. The building was designed by Field and Clegg Bradley Studios in 2005 and cost £1,800 per square metre. The intention of the site is to provide a healthy working environment for employees of the National Trust. The key features include ventilation snouts for active ventilation, PV panels for sustainable energy, a ripple wall to block direct sunlight, and an aluminium curtain for shade. These are some of the photos from our site visit.
The building has many passive design choices to help it achieve its goals. A folded aluminium curtain provides shade for the south facade to avoid any glare in the workspace. The styling of the shade mimics the folded roof design. The orientation of the building follows the existing local grid with a slice taken through the plan to create a south facade. This means that the building can capture a large amount of natural light while working aesthetically with the site. Heelis also has 42 ventilation snouts that provide stacked ventilation throughout, regardless of the weather conditions. The rippling curtain on the southwest, northwest and northeast facades helps to eliminate solar gain by blocking oblique sunlight from entering. This also helps to prevent glare. The natural lighting was both physically and computer modelled in the design stage to ensure that all areas of the workspace achieved ample natural light and glare was avoided throughout.
The active systems within the building mostly act to support the passive strategy. The main feature here is that the series of actuators, which are connected through the building management system to open and close the windows and roof panels inside the ventilation snout. The actuators work on an automated system which responds to the building's internal temperature and heating requirement, opening and closing when necessary. The ventilation snouts are also fitted with a mechanical ventilation heat recovery system, which reduces the heat loss and necessity for mechanical heating during the winter months. The system extracts stale warm air from the interior and fresh air is filtered into the building through inlets. The fresh air is then heated using the stale air, with warm fresh air being resupplied to the interior and the stale air being dispersed through the exhaust outlet. To reduce the amount of energy the building consumes from the grid, over 1,500 photovoltaic panels have been fitted to the south-facing slant of the roof. These were initially intended to supply 30% of the building's energy requirement. However, with the addition of the server room, this was reduced to 15%. At the time of design, a government grant was also available for PV panels, which has reduced the payback period on them. However, the most effective feature in terms of payback time has been the inclusion of dimmable lights. The building meets its 300 lux requirement on both floors the majority of the time, so having the lights on full brightness is often not necessary. Dimmable lights allow the minimum amount of energy to be expended whilst providing a suitable working environment.
Here are two sections through the building showing the light and ventilation at 12 on the summer and winter solstice. The main lighting strategy prioritises diffused northern light from the roof lights to naturally light the entire building while avoiding low-angle glare, which would be distracting for office work. Roof lights are used as they are 2.5 times more effective than traditional windows. An average daylight factor of 5% and an average lux of 300 was achieved across the majority of the building. Using light from above meant all desks got enough light for employees to work at, although one complaint was that the walls were not lit enough and therefore the rooms seemed dull while each desk had enough light. The roof lights are dimmable and supported by occupancy sensory lights, which turn on depending on whether people are in the room or not. This helps to save energy. Some areas of the building, such as the atrium, which is a breakout space for the employees, and the visitor space, have direct southern sunlight to create dynamic, vibrant spaces. However, for the working office spaces, the ripple wall protects the northwest windows from low-angle western light to avoid glare. The Heelis building is successful in naturally lighting a deep plan office with diffused natural light. For ventilation, the building uses a mixed approach between natural and mechanical, with natural cross ventilation from the two courtyards and stack ventilation from the mezzanine structure, allowing the free movement of air. Mechanical systems like the MVHR and fans support the natural ventilation and keep a stable temperature within a range. The building is heated partially by thermal massing. Along with the steel structure, cast concrete planks on both floors allow for thermal massing and in the roof. Due to this type of heating, the temperature in the building is variable across the day. One review of the building called the worker response to this a cardigan culture. Because of education about the building during the handover phase, the workers are happy to bring in a cardigan to wear when the building is cooler and take it off when it's warmer. The building does a purge of its heat at night to cool the building for the next day in the summer.
Despite the many successes of the environmental strategy, there have been some key issues which have arisen since the building handover through the post-occupancy report. The building has a gas boiler which produces 215 grams of CO2 per kilowatt hour of heat produced, which is far less efficient than alternatives such as a hybrid system, which could produce 11 grams per kilowatt hour. There have also been some issues with the passive and active systems interfering with one another. For instance, in winter, the windows have been triggered to open by the internal heating. In addition, the solar panels are working under their maximal potential as they are fixed to the roof, which is slanted at a 30-degree incline. PV panels work best when the sun angle is perpendicular to them, which has meant that they are performing suboptimally 75% of the year. Suggestions for how the building performance can be made even more efficient will be discussed at the end of the presentation.
Moving on to the life cycle of the building, we have focused on three main elements that are highlighted in the annotated section: the folded aluminium curtain, the steel frame and the glazing. Each element's life cycle is listed with a colour key indication. Yellow indicates the product, which is the raw material. Blue indicates construction, which is the manufacturing process. Red indicates operation, which is the materials use phase. And purple indicates the next life, which is how the material can be repurposed and reused. In terms of improving the building's life cycle, a greater use of low-embodied carbon materials, such as a timber glulam frame, could be used instead of steel. Secondly, the use of precast concrete instead of in-situ concrete on the ground floor, so that it can be easily reused or replaced. Finally, higher profile windows could also be incorporated to reduce thermal cold bridging.
The primary structure of the building is a steel frame which is bolted together. On the ground floor is an in-situ poured concrete slab, and then on the first floor we've got precast concrete floor panels, and then in the roof of the building we've also got precast concrete soffit panels with corrugated metal roofing sheets. So this is all bolted to the primary steel structure, apart from obviously on the ground floor the concrete floor is poured in. So in total the whole structure is bolted together, which makes it easier to dismantle at the end of the building's life, apart from the floor on the ground floor, which will need to be broken up separately. In the centre of the slide you can also see the diagram showing the load paths of the building. So the loads start in the roof, work their way down through the walls and across the floors until they get to foundation levels, where they spread evenly in the ground.
The majority of Heelis' construction was that of precast components which were craned in on site. The only in-situ component of the building is the concrete foundations, as mentioned in the life cycle analysis. The aluminium panels on the south facade were inspired by the railway works associated with the area. They were locally sourced, being sand cast in a Great Western Railway manufacturing plant in Melksham. The building's frame is made from steel beams and columns, which are entirely fixed through bolts and not welded in any areas, with conscious thought to the building's life cycle. Similarly, the concrete floor panels are precast, being lowered into place during construction. This also paid thought to the entire life cycle. The concrete soffits in the roof structure also assist the environmental strategy of the building by providing thermal mass which dissipates heat, helping cool the building overnight during the summer months and keeps the internal environment comfortable when the occupants return the next day.
Next is the glass and facade slide. this slide mainly focuses on the south facade of the building. The south facade is predominantly glass, which is on a secondary steel structure, which is then bolted to the primary structure of the building. Across the south facade, in parts, there's these big aluminium panels which are bolted across the front of the glass to help reduce solar gain in the building, as well as the overhanging roof, which includes folded metal blinds to help create a curtain which also contributes to reducing the solar gain of the building. And then next, on the other three sides of the building, the walls are solid and they're cladded with bricks to lower the embodied carbon of the building, and they also help to represent the industrial heritage of the site. Lime mortar is used with the brick cladding, which makes it easier to remove the bricks at the end of the building's life as well. And also, on the south facade, not much insulation could be used, obviously because it's so much glass, but on the other three facades of the building, a lot more insulation is used in the walls, and as you can see in the section in the middle, insulation is used in the roof where it can be between the ceiling and the corrugated metal roofing sheets.
Heelis doesn't use any smart materials as such, but the way that it implements materials throughout could definitely be considered as advanced. The timber cladding throughout the building and primarily in the atrium space uses wood sourced from fallen trees and National Trust estates across the country, which helps to reduce the embodied carbon. Recycled tin from beer cans is used in the shelter plates at the top of the ventilation snouts, which also benefits this. Another key material used is in the carpets in the workspace. The wool was sourced from herdwick sheep, which graze on many National Trust estates and, at the time, had a very low wool value. This helped the building financially and benefited the farmers that were struggling to sell the wool. There are, however, some improvements that could be made to the materiality. A higher gloss paint could have been used in the interior walls to help lighten the spaces, as in the post-occupancy report, it was noted that the space could feel a little dark at times despite the ample desk lighting. Another way to combat this could be using a lighter coloured carpet, but that could also lead to an increased need for cleaning in the building.
The Heelis building has 3 dedicated fire escape routes. These are shown here in red. They have fire-resistant walls and doors and escape out to the outside, straight from the building. The building is open plan, so any route can be taken to each of these from upstairs or downstairs. The building technically only needed 2 for its size and the amount of workers, but because of the kitchen, which created a dead end in the corner, they added a 3rd. Visitors can escape from the front, straight outside through multiple exits. There is access to all 4 sides of the building for fire engines, shown here in grey. On the southern side, it is a pedestrian route, but wide enough for a fire truck to go down in an emergency. From the most central point on the top floor, it would take a person aged 50 years old 52 seconds to escape at a quick-paced walk. The REBA 2030 Climate Challenge. The building was finished in 2005, so the embodied carbon wasn't recorded. The operational energy was the focus of this building, and this achieved 81 kilowatt hours per metre squared when the catering kitchen is discounted. The PV panels helped this building achieve such a low number. Despite the building not achieving the 2025 target, it is a very successful building for its time and almost meets this target.
A potential improvement to the building could be a glue-down frame compared to a steel structure. This is because it has a lower embodied carbon and is a non-corrosive material, resulting in lower maintenance. As well as a more elegant finish, glulam has an improved fire resistance and lower thermal conductivity, therefore reducing cold bridging.
Although the building's overall performance is very good, there are a few notable issues that could be resolved if the building were to be built again. Better communication in the building handover stage would help to reduce the energy consumption in the building, as appliances like the dishwasher were often left on all day. The natural lighting throughout the building is exemplary, as previously mentioned. However, the walls appeared dark in use due to lighting from above, which could be solved by more wall openings or a higher gloss paint.
Adding a new form of passive cooling for the server room could drastically improve the performance of the building, such as earth tube passive air conditioning. This would work well at Heelis due to the high clay content of the soil, making it slowly permeable. The flower bed outside the south facade of the building would be a suitable location for underground pipes to be fitted, and would offer assistance in the passive cooling when the flowers are watered. The server room uses 50% of the building's energy requirement as a result of cooling, so this would be one of the most beneficial changes that could be made. Similarly, the excessive heat from the server room is not currently recovered by the mechanical ventilation heat recovery system, which could also be fixed to further improve the building's efficiency in winter months, reducing heat loss. Underground pipes elsewhere could also be used to provide heating to assist the boiler through a ground source heat pump. Similarly, an electric boiler or hybrid system would reduce the building's carbon footprint, as a gas boiler currently produces all of the building's heating. Gas boilers produce nearly 20 times more carbon than a hybrid electric and ground source heat pump would. The solar panels could also have their efficiency increased through adding the ability to tilt the angle of them. If these would be able to be mechanically altered through the building management system, which also controls the roof ventilation and windows openings, they could be altered to maximise the solar harvesting base of the sun angle for that time of year. PV panels absorb the most energy when they are perpendicular to the sun angle. This would also help the shading, as the solar panels act as a barrier for excessive solar gain through the roof lights in the summer.
To conclude the presentation, the National Trust headquarters provides an excellent working environment with plenty of natural light and ventilation which reaches all points of the building. Light is even focused down onto desks where 5% daylight factor is achieved everywhere. Therefore, due to all the building's outstanding key features and design elements, it has been awarded an excellent BREEAM rating along with various other awards.